If you've ever wondered about the electrical logic behind an industrial air compressor, rotary screw type specifically, this video is going to be covering that. Maybe you work at a shop that has one. Maybe you work in maintenance and you've just never known how they work. Maybe you're interested in getting into this work as a career. If you end up liking this video, hit the like button. If you don't like it, tell me in the comments all about it. And if you're interested in air compressed systems and the industry in general, we will be covering many videos over the industry. So hit subscribe and maybe we can all learn together. Okay, so if you've ever been faced with the new challenge of learning an electrical system when you don't really have any prior knowledge with electrical, I can tell you it does look a little bit daunting at first. I mean, look at all these lines and the lettering and doesn't mean anything, doesn't mean nothing. The symbols, dash lines, partially dashed lines. So the only way you can really eat an elephant is one bite at a time. To do this learning, all you need to do is try. Put it in front of you daily, review on what you've remembered, and learn something new every single day. Now this electrical schematic we're going over is for an electrically powered air compressor driven by an electric motor, an induction motor. This diagram specifically is for a Ingersoll Rand R90i to R160i fixed speed compressor. Fixed speed means the main motor spins at a certain speed the whole time. It's a rotary screw type air compressor. It's air cooled. These are typically air cooled. There's some water cooled units, but they are few and far between because water-cooled presents its own problems. It's a contact-cooled unit, oil-flooded, versus oil-free. And the 90 and 160 in the model number stands for the kilowatt rating of the motor, which translated into horsepower is about 120 to 200 horsepower. If you don't know what all this means, see the video that I should have posted before this one about air compressor basics. So this compressor being electrically driven by an induction motor has three-phase alternating current coming in right up here, L123. This is typically in industry 460 volts. The 460 volt three-phase power is used to drive the main motor, MM is for main motor, and also used to drive the fan motor, FM is for fan motor. You can see that the fan motor power taps straight into the 460 coming out of your disconnect. Your main motor and your fan motor have different protection systems. Your fan motor and your main motor are started by the contactors. The KM1, KM2, and KM3 contactors are used to start your main motor slowly with minimal power at first, or half power. This is so the main motor does not have as much of a inrush current when drawing the amps to turn the motor, and it helps with the life of the motor long term. The fan motor uses a direct online system to start the motor, meaning it is just one contactor right here, KM4, to pull in to start the fan motor. The fan motor is not drawing nearly as much amps as the main motor on startup. Aside from the KM1 and KM2 and KM3 contactors on startup for the main motor, we also have a FR1, which is the FR1 is the overload for the main motor. I'm not sure why it's called FR1. I would have called it OL or something else. This is the designated symbol for the 50 hertz frequency. We don't use 50 hertz here in North America. The 60 hertz down here looks like it has white wires and black wires going to CTs, which is current transformers, being fed back to the FR1, and this is how it senses the current and will trip the compressor if there's an overcurrent situation. If the main motor is drawing more amperage than it is safe to draw. I'm not going to go into detail too much about UVW1 and UVW2. That's something that should be covered in main motor wiring video. Same here with a fan motor. So other parts that the 460 coming is used for is the K2 up here is an option. It's a phase monitor interrupt. There are a couple different designs for phase monitors. The one that we use has settings that you can set for the voltage that it's supposed to be monitoring, and over voltage situations, under voltage, and what to do if the voltage becomes unbalanced. Usually has 3 lines coming into it from the 460. It monitors the 460, making sure it stays in those ranges that you want it to stay at. If there is a phase imbalance or a loss of a leg or over voltage situation, it will trip the compressor if wired correctly. The usual way we trip a compressor is over here, I'm getting a little ahead of myself, but this ES1 is for the E-stop, the emergency stop switch. You press it, it will sever 120 volts going to the controller to turn off all these contactors. This is what actually runs the motors. KM1, 2, and 3, and 4 mentioned over here, we'll turn them off. Basically, the way you would wire this in is from, instead of going from the E-stop onto the controller, you would place it here in the line. There's a jumper between contacts 102 and 105. You would just take a wire from 102, put it over here to your normally open switch, and take a wire from 105 and put it over here to this terminal, and it'll bridge the gap as long as you have good power coming in. This contact will be on normally open, and power will go through to your controller so that you can run your compressor. And the last thing that is usually used for the 460 is you have to transform your 460 to 120 volts to power all of your 120 volt electrical components over here via the controller. And it also takes the 120 volts over here so that you can take 120 into your power supply and turn it into 12 volts for the controller to actually run, because this controller only runs on 12 volts DC. There are several places where you see MCB1, MCB2, MCB3. These are all miniature circuit breakers. They're circuit breakers just like the circuit breakers that come into your house that trip when there's an overcurrent situation. This miniature circuit breaker is the 460 coming into the transformer. It trips at 3 amps. For your phase monitor, it's something around half an amp. I'm not sure if you can see this in the video. I can barely see them on my screen. And this miniature circuit breaker is the 120 coming out of the transformer, and it trips at 6 amps. I'm not going to label all the MCBs. I'm labeling one right here, and you see what it is. So I marked these lines for 0 volt and 120 volt, your neutral and your 120. Like I mentioned before, the 120 comes over to the e-stop, goes through the e-stop. So the e-stop is used for two different things. There are red wires and blue wires going through it. Both contacts for those wires are normally closed, meaning you would normally as in when the e-stop is not being pushed in, not being hit, you would have 120 coming through the e-stop to your controller to power all your solenoids. The reasons you have the 120 in the e-stop here to cut it off when you hit the e-stop is so that it will stop powering the KM1 contactor and the KM2 contactor so that the main motor will pull out and stop turning. The other end of the e-stop is over here for the blue wires coming out of a controller and back into the controller. Whenever the controller senses that this has opened, you hit the e-stop, the connection opens, and there's no longer a signal coming back to the controller. The controller knows that you hit the e-stop. That's how it actually knows that there's an e-stop pressed versus you losing your 120 volts only and the e-stop was not pressed. The CDV here is for the condensate drain valve. It is an electronic drain valve to drain the condensate or the water coming out of your air after being cooled. It is a no-loss drain valve, meaning it senses when there's water in the valve, and it will then drain itself, draining only the water until your water is drained and then stop draining so that there's no air loss. All of these that are labeled SV are solenoid valves, meaning you apply a 120 volts alternating current to it from the controller and it turns into a magnet and it opens a valve that was otherwise closed, or closes a valve that was otherwise open, depends on the style. Even these that are not labeled SV, the KM1, KM2, KM3, these are still solenoids. They're still magnets that close the contactor and allow the power to flow to the motors when they are given energy. So anytime this is a running situation, these contactors are all powered. They all have 120 volts going to them, and that's the only way to keep the main motor and the fan motor running. I'm going to skip over the KM1, KM2, and KM3 contactor setup right here. I'm going to skip over it for now. I'll explain this at the end of the video if I have the energy. So the 4SV is actually the water shutoff valve, and it's only used on water-cooled units. Like I said, most units I see out in the field are not water, but in a normal situation, if it is on a water-cooled unit, it would be a normally closed valve, meaning it stops water when it's not energized from going to the unit. Whenever you turn the unit on, it energizes and it opens the valve. Because it is normally closed, it then opens the valve and water is allowed to flow through your unit, cooling the unit. Okay, now we're down here at FR1. I don't think I've actually seen this installed on this type of unit that I can remember in my head, but I'll try and explain it the best I can for how it's electrically explained right here. The FR1 shown down here is for 60 Hertz machines, which is machines we would be using here in North America. You see how the black and the white wires go to the CT current transformers on each of the legs. It doesn't actually connect to the 460 volts. I believe this unit is powered by 120 volts, which is why you see it up here tapping into the 0 and 120 volt leg power. It's here to protect the main motor from overcurrent. The current transformer is different from a voltage transformer. This transformer up here transforms your voltage from 460 to 120 to be used in the rest of your system, but a current transformer is different. It measures the flow of current through the conduit or through the wires to the motor, and it transforms the current at a certain ratio. It's given a CT ratio. If you see down here, for the motor sizes in this range, it gives a CT ratio of 200 to 5. If it's a 160 kilowatt unit, which is how I'm trying to explain this as, it's actually a CT ratio of 250 to 5. What does that mean? Well, let's get our calculator out. 250 divided by 5 is 50. Let's just say you had 200 amps of current flowing through the conduit that the CT is measuring. If you had 200 amps and you divide that by 50, it would give you a CT of 4. That 4 amps is what's going to be read here in the overload or the current protection system. You don't want it to transform the whole 200 amps that's going through the conduit over here. This little contraption is not going to handle that kind of energy flowing through it. It's not supposed to be designed for that. So you want it to transform to a very small amount of current that it can read. So in the situation, let's just say you want the current transformer or the overload or the current protection device to trip when the motor is pulling more than 250 amps through these wires. You would have to take the CT ratio, which we did 250 to 5, and that's 50. And in that situation, you would have 250 amps divided by your 50 you came up with. So in this situation, you would have 250 amps divided by that 50 from the CT ratio, and it would give you 5 amps. So if this protection device saw 5 amps flowing through it, you would want it to trip in that situation. And if maybe it was different, like at 260 flowing through this conduit, you would ask it to trip at 260 divided by 50 at 5.2 amps flowing through the overcurrent protection system. Now, if this did sense an overcurrent situation, this is where it would decide to trip it at. This controller will look for a closed loop between 11 and 12 going through FR1. This is a normally closed contact. So in the case of overcurrent situation flowing here, or sensed here with the current transformer, it would trip, open a little switch, the little switch being right here. There would be no signal coming through this normally closed loop, and the controller will trip the machine to protect the main motor from overcurrent. This PTC here is an optional piece system. The PTC is actually for the motor winding thermistors. A thermistor is a temperature measuring device, and the motor windings are inside the main motor. So it just measures the temperature that the motor is internally. These motors aren't supposed to heat up too much. If they feel very warm to the touch, you probably have a problem going on. At least if it's an induction motor, that's the case. I'm going to label this main motor overload. Okay, I've labeled the E-stop 120 volts AC, E-stop second switch blue wires, 24 volts DC, PTC being the main motor thermistor over temp situation. FMP stands for fan motor protector. FMP, fan motor, okay, so the fan motor protector doesn't quite work the way a main motor protector overload does. The overload keeps a closed switch over here to show a closed loop. The CDE is for condensate drain error. It's the optional unit mentioned over here, the electronic drain valve. It's normally closed loop and it opens whenever there is a drain error with the electronic drain. RSP is for remote stop. RST is remote start. These are all options, and I can't find RLL, RLE, RLU in the in the manual that I'm looking at, so I'm just not going to mention them. They're very seldom used anyway. These over here are your transducers. Transducer is just a fancy word to throw around to people who don't know what a transducer means. It just means that it's taking a physical pressure and sending it as a signal to your controller, basically, so that the controller knows what pressure is going on at what stage of your system. One AVPT is the air vacuum pressure transducer. This is used when your main motor is turning, sucking in air in the air end to make air compression. There's a small vacuum between where your air end is pulling in air and your air filter is cleaning out the air, filtering the air, so that your compressor doesn't take in dirty air, dusty air from outside. The more dirtied your air filter becomes, the more of a vacuum there is between the air filter and the air end. So these compressors will usually show an alarm whenever there's too much of an air vacuum so that you know when to replace your air filter. 3 APT is a wet sump pressure. The sump is where your air is coming in with your oil in this case, because this is an oil flooded unit. When this machine is running but not making air, your sump pressure might be around 18 to 26 maybe sump pressure, and it's wet sump pressure because this sump pressure is taken before the oil separation. The oil gets separated from the air, passed through your oil separator, and on the other side of the oil separator would be considered dry sump pressure. It's the sump pressure after the oil is taken out of your air. Sometimes that is measured in a system, the difference between your wet sump pressure and your dry sump pressure, or pressure right after the separation process, because when there's a large difference between the two, you know that there's a blockage in your separator, or your separator is filthy and you need to replace it. 4 APT is your package discharge pressure. It's the pressure of the air that's going out of the compressor into the system. And basically, usually it just means it's system pressure at the air compressor, right where it goes into your customer's air system. So your 5 CPT and 6 CPT is your coolant filter in pressure and your coolant filter out pressure. The coolant filter filters your oil to keep it nice and clean. It's very important with a oil flooded unit because the air that's coming in isn't always nice and clean, and the air might have chemicals in it. The chemicals will mix with your oil because the oil mixes with your air at the air end for an oil flooded unit. So the coolant filter can get stopped up, and if there's too high of a pressure difference or a pressure delta between 5 CPT and 6 CPT, the compressor will throw an alarm. 10 APT is remote air pressure, remote as in sensing air pressure at a remote location away from the air compressor. I've seldom seen this used, and that's why it's seen here as an option. Alright, the CTT and ATTs down here. The TT stands for temperature thermistor. The C is for coolant. The A's are for air. So 2CT is a coolant temperature thermistor, also is 3CTT. 2ATT is an air temperature thermistor, and 4ATT is an air temperature thermistor. So 2CTT is injected cooling temp. It measures the temperature of the coolant that is getting injected into the air end to mix with air coming in before compression. 2ATT is air end discharge temp. It's measuring the temperature of the air/oil coming out of your air end after compression. 4ATT is measuring your package discharge temperature, the temperature of the air coming out of the package, out of the air compressor before it goes into the system. And 3CTT is coolant cooler out, and it is only used when there is a smart thermal valve installed. And 1ATT is a temperature for the inlet coming into the machine before compression, and it's also only used when there's a smart thermal valve installed. This CFO over here is for common fault output. Basically, if this controller senses a situation where it thinks something's faulty, it will open or close some of these contacts to alarm someone far away that there's something wrong with the compressor. So now we're up here at the solenoids, 120 volt powered solenoids. So when you have the motor turning, it doesn't really, the motor just turns usually. It doesn't suck in air and actually create compression unless it's allowed to open a valve, in this case the load valve, to allow air into the system and it be compressed. So the 1SV is for the load valve. To make a long story short, you energize the load valve and the unit starts taking in air, loading the machine or putting a load on the motor and the air end, the load being air compression. The 5SV is the modulation valve. It's optional. And what modulation is it's a different option than just loading the machine. You just load a machine and it takes in all the air it can get, or all the air it's allowed. The modulation valve is a little different. It will open the valve letting air into the machine a certain amount to allow a certain amount of air in, so only a certain amount of air can be compressed. It saves the motor from using a high amount of amps when you don't necessarily need that high amount of amps. It's meant to save money because if you're only allowing in half the air the motor can take and you only need half the air the motor can take, then you'll be using less amps compressing half the air. You won't be using half the amps, but you'll be saving some money nonetheless. Number 9 is the condensate drain valve. It is different than the CDV up here. The condensate drain valve up here is an electronic drain valve that senses the water level and discharges only the water. This condensate drain valve does no sensing whatsoever. It's set on a timer by the controller to open the valve every certain amount of minutes for a certain amount of seconds. This might have to be adjusted depending on the humidity and how much air you're compressing. If it's a dry day and your employees are not doing a lot of work, maybe it's a Saturday, then it can be set to rarely go off. If it's a humid day and it's Monday morning, maybe you would want it to be set on more often so that your air compressor doesn't fill with condensate, and you want to discharge all the water you have, but you don't want to lose too much air. K3 is the blower drive control relay. Whenever you energize K3, the auxiliary contactor on K3, named K3-1, will close right here, and the fan drive will turn on if it's installed with one. Not all machines have them. What this basically does is, instead of sending main power to your fan motor to just spin it at its normal speed, this drive will actually change the speed of the motor at the request of the controller. The Poro right here is the power outage restart option. If you lose power and you have Poro set up, your controller will wake up after power comes back, say, hey, I was running, maybe I should be running again, and it will restart the machine after sounding an alarm. This is a speaker right here. It's optional, doesn't come on the machine unless you request it. KM4 is the fan contactor we mentioned before over here, bringing 460 to power your fan motor. Alright, now this is probably the most difficult part to understand when I started learning this system. I know it's the part I had the most trouble with when I started learning this system. I understand it now, but it's hard for me to imagine that I could explain it and somebody understand it immediately. It's a little hard to explain and hard for people to get the first time around. You might have to visit this a couple times to understand how the KM1, KM2, and KM3 contactors all together start the main motor only. It's called a star delta system. Let me explain. Okay, so the first thing I need to make very clear is KM1 is right here. KM2 is right here, KM3 is right here. These are the contactors that send power to the motor. They also have auxiliary contactors on the sides of them or on the front of them. They are labeled KM32, KM11, KM31, KM21. What this really means is KM21 is the first auxiliary contactor on KM2. So even though this here wire is lined together with KM3, this contacting is physically on KM2. It's normally closed. That means that whenever KM2 is just chilling with no power applied, it is closed, meaning power goes through to it. So in a normally off situation, the only of these wires that's actually going through is KM3. So when the unit starts, the first thing it does is it sends power through pin 3 to KM3 contactor. When that happens, KM3 pulls in, and any auxiliary contactors that are on KM3 change state. So which auxiliary contactors do we have on the side of KM3? Well, this one is named KM32, so this one is this auxiliary contactor is physically on the side of KM3, as is KM31. So whenever this contactor gets power and pulls in, KM32 opens, KM31 closes. So that means right when KM3 pulls in, power is allowed to flow from pin 2 through KM31, but not to start KM2 because KM32 opened when KM3 activated. But instead, it can flow through KM31 to KM1 contactor, and this contactor pulls in. So the time between KM3 pulling in and power flowing through KM31 to power KM1 is a time of maybe a tenth of a second. And when that happens, KM1 pulls in, so any auxiliary contactors on KM1 also change state. That means this KM11, which is actually on KM1, closes. That means power is not only allowed to flow down from KM31 to KM1, but KM11 is allowing power to itself through its own auxiliary contactor, which would now be closed. So KM1 is doing his own thing at this point. Some time goes by for the star delta system, and then the controller decides, okay, it's time to pull in the other contactor, KM2. What happens is it removes power from this 3-pin, and then KM3 no longer has power. It turns off. It opens, and all of the contactors that were previously changed state now go back to their normal state, their off state. So KM32, which was just open, because this was just in a different state, now goes back to its normal state, which is closed right here. KM32 is closed. That means the power coming through pin 2 powering KM1 also can go down and power KM2. Since this contactor turned off, KM3 is now open, and KM21 is now gonna open because its normal state is closed, but now KM2, which is where the KM21 contactor is activated. So it switches states to open. It does this so that the KM3 contactor will not pull in when this is pulled in. And the reason that the KM31 contactor opens here when this de-energizes is partially also because you don't want KM2 to stay pulled in if something happens to KM1. You need these both pulled in together. So the only way for KM2 to get its power is if KM1 stays closed, meaning if this stays energized. If this ever opens and lose its power, this switch will also open, and KM2 will also open because that was the only chance it had to get power from pin 2. And we're going to label this star delta starting. KM1, KM2, KM3. Alright, I think I pretty much covered everything within reason. The only reason I did this is because my cousin is interested in the industry and I don't really have time to go to his house and teach him. He doesn't really have the time for us to get together either. So I figure I wanted to make YouTube videos. I'll just put these out so he can watch them. If he has any questions, he can let me know. If you guys have any questions, let me know. I can cover videos across different air compressed systems. We can do some dryers, heated dryers. We also work on refrigerated air dryers. We work on lower pressure units also, and I work on centrifugal air compressors. Don't think there's going to be much of a need for centrifugal air compressor videos though. There are far more rotary screw industrial air compressors out there than there is centrifugal air compressors. I plan to make another video with the air piping and instrumentation for this exact same unit to explain where the air, oil, and condensate flows throughout the system, where it changes, and what kind of temperatures you'd see in what places for this unit.